So we will start from the same point where we finished last time. We were discussing about the condition for the stability. And if we just recall, the condition for the stability was this thing that in a negative feedback system where we have a some signal coming into our black box, and what's happening is going to be multiplied by some feed forward gain, which was HS in this case, and then there is a feedback gain K in the negative feedback. And we want to write the expression, what will be the overall net transfer function, that will be H of S divided by 1 plus K times H of S. And if we observe this thing, the system will become unstable, or this will be equivalent to infinity if we put K times H of S as -1. If this factor becomes -1, this H of S divided by 1 plus K H of S, the whole transfer function, if I want to call it as a G of S, for example, this will become infinity. This means the system becomes unstable. And that is a condition for an unstable system. Now, how we define this unstable system using the Bode plot or using a magnitude and a phase response, that we mentioned. Okay, if this K times H J of omega is, for example, -1 for us, then this means that my magnitude response, my magnitude response is going to be in the terms of 20 log, it's going to be 0 dB, or the magnitude will be 1, and my phase is -180 degree. So if both of these things coexist together, this means this is equivalent to K times Hj omega -1, and this ultimately means my system is going to be a unstable system, or it's a positive feedback instead of a negative feedback. So this is the condition for stability, and that's what we need to make sure we don't go into this era. So in this point we finished last time, so we are going to start building from this point, and we'll see how we can check the stability condition. So for the stability condition, we can now safely write, instead of K times H J omega as 1, we can write K times H J omega greater than equal to 1. If my K times H J omega, which is a loop transmission gain, is equal to or greater than 1, and my angle, phase angle, is -180 degree. This phase angle is for the K times H J omega, not for H J omega. It should be from K times H J omega. If it is -180 degree, this means my negative feedback system will oscillate, or in turn, it is not a stable system. So for any like a feedback amplifier, I don't want this to happen. These two conditions shouldn't exist together. So we need to find how we can decide these things, or even if the stable system is unstable, how I can rectify that one in the amplifier. So that's what we are going to see with the help of some examples. So just to reiterate, to ensure stability, we must ensure that these two conditions don't occur at same frequency. Okay. So how to mention this thing pictorially? So if we see this plot, the top one is a magnitude plot, and this one is the phasor plot. So if we see this one, we have a magnitude plot in which the omega is varying, and we have a frequency omega 1 where the pole is, let's say, existent. And we have that one, or the desired frequency is omega 1. And at omega 1, we need to see the magnitude response. What is the value of magnitude response? And at the same frequency, we need to see what is the phase value. So at omega 1, we are going to see our magnitude value, and we need to see our phase value. And based on that, we need to decide whether the system is stable or not stable. So if we see the magnitude response, what we can see, is it a positive value? Is it a 1? Is it what? So if we see a little bit carefully, we know this is 0 dB. So this means above 0 dB, anything is going to be positive. So what we can say, that K times H J omega is greater than 1. If K times H J omega is greater than 1, condition for instability is there. If the other condition coincide with this meaning the phase response is minus 180 degree, this means this system or this plot is for an unstable feedback system. So let's see the other one. And the phase one is telling what? At omega 1, the phase is having a value of minus 180 degree. This means the other condition also retrieves that this system is an unstable system. So we need to see a magnitude response and we need to see a phase response at the same frequency to get us idea about whether the system is stable or not stable. So from this analogy, we can say this system is clearly an unstable system. Clear hai yahan tak point? How this system is unstable and how we are seeing these magnitude and phase plot. We will see another small pictorial representation, and I would like all of you to just pay attention yourself. For example, if we talk about this plot, we have two frequencies, omega 1 and omega 2. So the top one is again magnitude response, it's 20 log, and this one is a phasor. Okay. So if we talk about the top one, it has two frequency points, omega 1 and omega 2. And the down one, the phasor response, also has corresponding two frequency points. So can anyone see what about omega 1? We have two frequencies, so we need to check about both these two frequency points, omega 1 and omega 2. What about omega 1? Is it a stable or not stable? So
sir, it should be stable because the value of the magnitude is not greater than or equal to 1, and the angle is also not minus 180. So it should be stable, I guess.
yeah, so there is one just correction. The magnitude is 1 basically because 0 dB means it's equal to 1. Okay, this is a 0 dB. 0 dB means that the value k h j omega magnitude is 1. So magnitude is 1. Okay, but on the other side, phase is minus 160 degree. This means it's less than minus 180 degree. So on the phase side, yes, it's not. And when both of these conditions don't occur concurrently or in parallel, this means the system is stable. So we can say the system is stable for omega 1. Okay. So this line, just to reiterate, this is a log scale. So this line is 0 dB means magnitude of 1. And if we see omega 2, the phase is minus 180 degree. Again, one condition of instability is there. But if we see the magnitude, since this is 0 dB, this is going to be positive, this is going to be negative. So the magnitude is going to be negative, a smaller value. This means omega 2 is also not unstable. I guess somebody raised hand. Can
Sir, what if the magnitude was 1 and the angle was less than minus 180, for example, minus 200 degrees? So would it be unstable then too?
If, for example, magnitude is less than 1, okay.
No, it's 1 and the angle is less than minus 180, for example, minus 200.
Minus 1, the system will be still unstable.
Oh, okay. Thank you, sir.
But we are just at this moment seeing in one perspective, but in the other scenario also the system is going to be unstable. So this brings us to a notion of some further definitions which we need to be careful that there is one terminology known as gain crossover frequency and another terminology of phase crossover frequency. So the gain crossover frequency, which your book is mentioning as WGOX, is the frequency at which the magnitude response crosses the 0 dB. Okay, so this point, which is omega 1 here, is the gain crossover frequency. Why? Because it is crossing the magnitude of 0 dB or a unity gain frequency, let's say. So this is a gain crossover frequency. Similarly, we have a phase crossover frequency whenever at the frequency at which we have a phase of minus 180 degree. So among omega 1 and omega 2 is the point where the frequency, where the phase is minus 180 degree. So omega 2 is going to be a phase crossover frequency and omega 1 will be a gain crossover frequency for us. This gain crossover frequency and phase crossover frequency are clear? moving forward, we can say for stability, we can a little bit relax or a little bit more mathematically express our definition that the gain crossover frequency should be less than phase crossover frequency. And that will cover that content which you are saying, even if it's a minus 220 degree, whether the system will stable or not stable. No, the system will be unstable because the gain crossover frequency should be less than phase crossover frequency. If they are not, this means the system is not stable. I would like all of you to just pay 1 minute and see about this thing, that omega gx should be less than omega px for system to be stable. Just try to digest this point using these plots. Basically, this is very much important whenever we have some problem. The example which we are just going to do now, it's going to relate these things, that how the system is going to be not stable. Okay. Afaq, you have any question?
No, sir.
Okay. So there is one question on the chat came, that how the magnitude and the phase can be seen together, or how we can. Let me just open that. So we can. The question is basically how magnitude can be compared to phase. Okay. So what we can normally do whenever we need to compare the magnitude and phase, we are going to see at the same frequency. For example, here we saw about the omega 1. Omega 1 is the frequency where our gain crossover is coming, meaning where the frequency is touching 0 dB. So we go to that frequency and we are laying down the phase response just next to each other. So at this frequency, omega 1, we are going to see the phase response. Okay. And what the phase response is going to be at omega 1 frequency, we are going to see the angle at which we are. If we see this angle where this line, if we draw this dotted line to omega 1 to this line, we are coming that this angle is minus 160 degree. Okay. When we see this thing, this angle is minus 160 degree. This means at this moment, the system is stable. Why? Because it didn't touch minus 180 degree. Okay. Similarly, if we are having another frequency, omega 2, and we are told, okay, at omega 2, see whether the system is stable or not stable. Again, we are going for omega 2. We are seeing the value of magnitude. The value of magnitude at this moment is basically less than 1, because under 0 dB scale. So it's less than 1. So we are going to see this value at the phase response. And when we see this thing, we see the phase is minus 180 degree. Again, the both conditions are not meeting. The system is again stable. So for both of these conditions, the system is stable. Now coming back to the second point, that for a system to be stable, we finalize that the omega gx should be less than omega px. Now let's apply here. इस केस में आपके पास omega gx क्या था, which is omega 1. What was omega px, which is omega 2, right? And we can see from this point omega 1 is less than omega 2, and that's why the system is stable. That's again for any system, we can all the time check this condition. If my gain crossover frequency is less than phase crossover frequency, my system is going to be stable. At least can be marginally stable, but at least it's not meeting that requirement of unstable where the system starts oscillating directly. If these points are clear, we can do one example, but before doing one like a example which is more detailed, but I would highly like all of you to go through these two examples from your book, that is 12.36 and 12.37. They're like a pretty much straightforward, but just to have a good practice to clear some concepts about the phase and the gain again. But make sure to go through, even if you don't want to do on a paper and pencil, but at least skim through 12.36 and 12.37. Now let's do one problem together. It's an example 12.38 from the book, and it's talking about this gain crossover frequency, phase crossover frequency, and also mentioning about how to ensure the system is stable or not. And if not, how you can make the system stable. Now we are talking in terms of our amplifier, which we have previously discussed and which we are seeing in this content. Let's start with the question. The question is basically saying that this is a open loop system for us. So this is, let's say, 8j omega, which is given to us. And they're saying we need to apply this system to a unity feedback system, meaning we need to have this 8j omega. This is V, final V out, let's say. So we are going to have a unity feedback system where this is 1 now. It's a negative feedback. ठीक है? तो ये आपके पास जो V in था, and this is Vs. ठीक है? So the problem is this one. So you have 8j of omega given to us, and you have k, which is equal to 1 in this case. And we are told to neglect other capacitances which are not given, meaning we are ignoring the parasitic capacitance or any other capacitance. Only we need to consider the C1, C2, and C3, which are there for us. And we need to plot the frequency response of the circuit. We need to plot the frequency response, A part. Okay, and B part, we need to basically determine the condition for stability. Anyone have any concern on posing the problem or what the question is asking? Just please ask, otherwise we will continue. So first,
how did you draw this feedback with unity gain exactly from the schematic to?
It's basically given the circuit is only open loop 8j of omega. जो आपके पास circuit है drawn in the black, this is only 8j of omega that is given to us. ठीक है? तो ये चीज हमें given है, and in the question they are writing that it's a unity feedback system. Unity feedback system meaning जो k की value है that is equal to 1. So this is just like what is given. I'm just drawing. I'm not like anything extra I'm doing. This is not drawn in the example. That's drawn in the red form, but that's the terminology they are using. We wish to apply a negative feedback with k equal to 1 around the 3 stage shown in this figure, which is a black. So this is an open loop, the black one, and then I am just applying a negative feedback with a unity gain. Clear point?
Okay. Okay, thank you.
Right. So first thing we need to do a frequency response plot. So frequency response किस तरह इसका होगा? If we just want to do A part. So there will be some. जब frequency response की बात आएगी, now frequency response means we need to do a Bode plot having both magnitude and phase response. Okay. Initially we were only talking about magnitude, but now since we have covered, so whenever it's said frequency response, this means both magnitude and a phase response. So this is going to be an omega, and this is going to be something. यहाँ से कहीं से शुरू होगा, and then it's going to be down like this. Okay. So this is going to be some point. That's a 3 dB frequency. This is a magnitude response, so I can safely say this thing as. Is question में k times 8j of omega or only 8j of omega is going to be same thing. Agreed? Since a unity feedback system, so k times 8j omega magnitude 20 log will be equal to 20 log 8j omega. Clear है यहाँ तक? So now we need to mention these 2 points.
Could you re-explain this diagram?
Right.
सर आपने unity gain को कैसे relate किया इस graph के साथ?
मैंने अभी unity gain को relate नहीं किया. I just said since it's a unity gain system, so what I can safely write k times 8, क्योंकि मैं loop transmission gain है यही draw करता हूँ ना, k times 8j of omega, right? Since k is 1, I can write this thing. मैं लिख सकता हूँ?
Yes, sir.
So I'm just drawing this thing at this moment. I didn't put any values that we need to discuss. के ये start कहाँ से होगा? इसके ये 3 dB point क्या है? All these things we still need to discuss.
Okay, sir. Thank you.
but generic picture is going to be like this. And also one more thing which is given to us, that C1 is equal to C2 is equal to C3 and all RDs are same. If we know this thing, first thing, can anyone tell me what will be the gain or the DC gain or the low frequency gain of this system? इसमें आप capacitors को ना include करें, क्या होगा? And also if M1 is equal to M2 is equal to M3, they are identical. What will be the DC gain, let's say? ये 3 stage एक amplifier है, what will be the DC gain here?
Minus 3 GMRD.
Sorry again. Minus
3 GMRD.
It's going to be a little bit near, so they will, because they are in cascade. So हम लोग कह सकते हैं log में कहें तो that, but you are saying also, so it's GMRD whole cube minus sign, because they are cascading each other, so we can safely write this thing. So I'm not taking the log at this moment. So this point, अगर इस magnitude की बात करें, this will be 20 log whatever the value is going to come, GMRD whole cube. ठीक है, क्योंकि ये DC gain है, so it's a starting point. Clear है ये चीज यहाँ तक? Just see the circuit again. We have 3 stages. So GMRD here, GMRD, GMRD. Since we are only talking initially about the DC gain, so we will make this C1, C2, and C3 as open. We are not going to consider these capacitances. So the DC gain, meaning at a low frequency, we are starting with the point something GMRD cube multiplied by, or we should take the 20 log of that value. Okay? So if we just 20 log 3 will definitely come, so we can have, but at this moment we're not concerned much about exact values. Then the second question comes, what is about this pole value? ये एक pole है 3 dB का, इसकी क्या value होगी? यहाँ ये किस frequency पे touch कर रहा होगा? यहाँ मैं क्या लिखूं? And what about minus something per decade? ये दो चीजें हैं. एक तो ये पोल किस लोकेशन पे होगा, इसकी फ्रीक्वेंसी क्या होगी, मींस इन टर्म्स ऑफ नॉट क्वांटिटेटिव वैल्यू बट क्वालिटेटिव एक्सप्रेशन, एंड आल्सो ये कितने डीबी पर डिकेड से डिक्रीज कर रहा होगा, इसकी स्लोप क्या होगी. कैन एनीवन वांट टू ऐड दिस थिंग? पहले
slope will be minus 60. Slope will be minus 60 perhaps.
So slope will be minus 60. That 100% correct, because all 3 of them are identical, so they will lie exactly at the same point. So ये सारे 3 poles एक ही point पे lie कर रहे हैं, तो 3 poles will minus 20, minus 20, minus 20. They will have a minus 60 dB per decade. That's fine. And what about the frequency? His frequency
1 over R naught C.
Yeah.
Something
So
like that.
here basically R naught is infinite, so it's an RD. So we can say this is 1 over RD. C or C1 कहना चाहें, but it's going to be 1 over RD C1. ये उसी तरह हम लोग find कर रहे हैं कि we are just across the capacitor, we are shunting it and we are finding what is the impedance at this capacitor. So यहाँ इसमें देखेंगे it will be R naught in parallel with RD. R naught is infinite, if for example, then it will be RD in parallel in multiplication with C1. So that will be the pole location, and all the 3 poles are lying at the same point. So this complete.
Sir, one question.
जी जी बताएं.
Sir, could you explain the gradient value minus 60 for dB by DC? Could you explain how do we get minus 60?
In this 3-stage amplifier, कितने poles हैं आपके पास?
3 sir.
3 poles. अगर 3 poles net हो तो net उनका response कितना होगा? एक pole का minus 20 dB per decade होता है.
Yes sir.
3 poles
तो cascade में,
so they are going to be minus 60 dB per decade.
okay,
But one thing important for us, from where they are starting, since all of them are identical, we said C1 is equal to C2 is equal to C3, and also M1 is equal to M2 is equal to M3, and also the RDs are same. So the main thing is that all of them will lie exactly at the same point. ठीक है.
Okay.
अगर सेम पॉइंट पर करेंगे तो दे विल स्टार्ट एग्जैक्टली -60 dB per decade instead of -20 and then become -40 and then -60. So they will start from
Okay.
the same point because it's given to us. अगर इन दोनों में कुछ
Thank you,
difference होता 10 times का factor or whatever, then we have to evaluate that correctly and then we say -20, then become -40, then -60. But in this case, it's -60 dB per decade. ठीक है. So this brings us to the first solution that, okay, we did the frequency response plot, but can we do the phasor response now? That's also one of the most important. Phase का अगर हम response draw करना चाहें, again drawing exactly at the same point, we have this one. So let me just draw it. So we know there are 3 poles, so we will go towards the maximum angle of -270 degree. There is no zero. So anybody want to help me how we can plot it? इसको मैं कहाँ से start करूं? अगर ये मुझे पता है, this is RDC1, this is the point at which the pole is existing, all 3 of. So इस point पे gain phase कितना होगा? At RDC1. Since there are 3 poles, अगर एक pole होता तो it will be -45 degree. Because
-135.
Yeah. So because of 3 poles coexistence, so it's going to be -135 degree. और यहाँ तक इसका कितना आएगा? -135 degree per decade. तो अगर मैं इसको यहाँ से start करता हूँ, this is 1/10th of whatever RDC1 location है, for example. So it will start from here. Before that it will be 0. So it will be -135 degree per decade से जाएगा. It will go continue at this scale until it reaches -2670 degree and then it will flatten. और ये किस point पे होगा? 10 times of 1 over RDC1. ठीक है. So this point is basically this point and this is this point. जी मिनाहिल.
सर हम एक पोल के लिए -1/10 ऑफ 1 ओवर RD के ऊपर हम -45 प्लॉट करते हैं. तो अभी इस पॉइंट आपने क्या प्लॉट
हम लोग -45 तब करते हैं when the pole at the same point exists. 1/10 से हम उसको start करते हैं. Meaning अगर जिस point पे pole exist करता है, tan inverse omega over omega p. So जिस point पे वो exist करता है, at that moment we say it 1 and we say if omega is equal to omega p, it's going to be 45 degree. ठीक है. So the point where the pole exists, we do -45 degree. इस पे 3 pole exist कर रहे हैं, that's why we are going -135 degree. 10 times lesser we start decaying the signal. हम लोग उसको -45 से in single pole case we start decaying down with -45 degree slope. But in this scenario, since there are 3 poles, so 1/10 points say we will start decaying down with -135 degree per decade slope के साथ. We start 1/10 से करेंगे, but we are going to start the slope at this point. ये clear है point?
Yes sir, thank you.
So this like covers the overall response. जी हमजा.
Yes, sir. I wanted to ask, when we're judging the stability as we did here, we do not have to make plots for the entire feedback loop transfer function. We will only have to do it for k8 j omega, right?
We all the time have to do for the loop transmission gain, which is k8 j omega. We don't have to do for the feedback loop. That's the main benefit, or that's a strong point that we know all the time have to go to check for the stability. आपको कभी complete feedback नहीं बनाना, आपको सिर्फ loop transmission gain meaning k times 8 j omega का ही बनाना है हमेशा.
Okay, sir. Thank you.
Right. So now the second thing is the condition for stability. The first and the natural question, is this system stable? हम लोगों ने देखना क्या है?
Unstable. It's unstable.
Yeah, so this is somehow our gain crossover frequency. Agar GMRD positive value hai magnitude ka, this is somehow is going to be a gain crossover frequency. So if we do the gain crossover frequency and we check the response, तो क्या उसमें value आ रही है? The angle is minus 270 degree. It's bigger or smaller in terms of magnitude is bigger than minus 180. This means the system is unstable. It should be less than minus 180 degree at least. अगर नहीं है, so this means the system is unstable. सेकेंड क्वेश्चन आता है कि ये सिस्टम को स्टेबल किस तरह किया जा सकता है, द थिंग व्हिच वाज गिवन कंडीशन फॉर स्टेबिलिटी. सो लेट्स वर्क अराउंड द कंडीशन ऑफ स्टेबिलिटी एंड हाउ वी कैन मेक और गारंटी दिस सिस्टम व्हिच इज गोइंग टू बी अ स्टेबल सिस्टम. लेट मी ड्रॉ वन diagram and then we can discuss it. I just did, let me, this let's say 0 degree. यहीं से हम लोग start कर देते हैं.
Sir,
जी बताइएगा.
could you repeat last part? वो unstable क्यों था? I just was unable to understand that.
Okay, just 1 second. I will just draw this one and then I will explain together again. So I draw करके and I will just explain that point. Yeah, so let's come back to the old picture. So we are here, this system, and we need to see the stability condition. Okay, so stability की condition के लिए हम लोग क्या कर सकते हैं? We can do one thing or we can do multiple things. We can go either at the point where it's crossing the 0 dB. ठीक है, आप लोग 0 dB देखेंगे gain crossover frequency and you will see what's happening with the phase that time. अगर मैं इस frequency पे देखूं, which is कोई भी frequency है, इसको die down करूं, नीचे ले जाऊं, phase पे इसकी value क्या आ रही है? minus 270 degree. So it is way beyond minus 180 degree. This means the system is unstable. Or vice versa, how I can see? I need to see phase crossover frequency. Phase crossover frequency कौन सी होती है? जिस पे phase minus 180 degree होगा. So I go back here, इस point पे, तो ये point है, इस point पे I check what is my magnitude. मेरा magnitude इस पे क्या है? Something here greater than 1. So at minus 180 degree, if my magnitude is greater than 1, this means my system is unstable. So किसी तरह भी check कर सकते हैं, either through gain crossover or either through a phase crossover. जी Ali.
Thank you.
So now bringing the same notion here. If we want to ensure how we can make this system stable, we need to draw this plot. ये प्लॉट हमें अब क्या बता रहा है कि अगर मैं फेज क्रॉसओवर फ्रीक्वेंसी को देखूं at pole 1 over RDC1, this point पे my phase is minus 135 degree. All of you are comfortable? ये वही प्लॉट है, minus 135 degree. फेज क्रॉसओवर फ्रीक्वेंसी कहाँ होगी? जहां ये वैल्यू minus 180 degree टच किया. So any point where this is touching minus 180 degree, that will be a phase crossover point. तो ये phase crossover point. इस फेज क्रॉसओवर पे होना क्या चाहिए? I will go back to my magnitude plot. ये कोई पॉइंट है and I want my magnitude to be less than 1. अगर वो magnitude मेरा less than 1 होगा, this means my system is stable. अगर नहीं होगा, this means my system is unstable. Currently the system is unstable. But if somehow I tweak my gain and do something with my gain that make it less than 1, might be we can make sure that system can be stable. So at this moment, in this current scenario, we are only going to create a hypothetical equation that if we want to make this system stable, how we can do that. But in the next examples, we are going to see a frequency compensation techniques to ensure or to make the system stable, what we should do. But currently, just keeping the same thing, we don't want to change anything on the circuit. We just want to play with the gain, that how we can make the system stable even in the current circumstances. Okay? So that is something. So what we want at this phase crossover frequency omega px, which is phase of minus 180 degree, we want the gain hp magnitude to be less than 1. Okay? If it's greater than equal to 1, this means my system is unstable. If it is less than 1, this means my system is stable. So that is the condition we know. So we are going to see how this HP can be less than 1. So I will write the expression for it. If I want to write H of S, like in terms of both low frequency and high frequency response, the overall net response is going to be this thing. Magnitude की अगर बात करें, ये ट्रांसफर फंक्शन ठीक है H of S का, जो हम लोगों ने सर्किट देखा था. नाउ ये वाला पार्ट लो फ्रीक्वेंसी को कर रहा है, दिस इज ओवरऑल काउंटिंग फॉर एनी फ्रीक्वेंसी, जो हम लोग पहले देख चुके हैं. तीन पोल्स हैं, all of these 3 poles are lying at the same pole location, so we are taking the triplet of this, and we know the omega p is equal to rd times c या c1 inverse. ठीक है, and the phase transfer function we can write hg of omega equal to 3 tan inverse omega by omega p. This is also telling the same thing, why the angle was minus 135 is 3 times of that one कि हमारे पास phase response इतना हो जाएगा. ठीक है, since there are 3 poles lying together. So if we want to find the phase crossover frequency omega px पे ये angle कितना होता है? This angle is minus 180 degree. So I can replace this thing as minus 180 degree, and I can do this thing minus tan inverse omega क्या बन जाएगा आपके पास? All of you are comfortable with this condition? इसमें कोई issue तो नहीं है जो मैंने यहाँ लिखा है. So I just replace, I want to find the relation between omega px and omega p, meaning I want to find the relation between the pole location and the phase crossover frequency. So what I am doing, I'm replacing my angle with minus 180 degree. If you minus 180 degree go, this omega is going to be phase crossover frequency. So I'm just replacing with omega px. Now if we do small manipulation, it will be 60 degree will be equal to tan inverse omega px by omega p, and this अगर हम tan इस तरफ ले जाएंगे, this will comes out to be omega px will be equal to under root 3 times omega p. तो देखिएगा इसमें कोई इशू तो नहीं है. If there is no issue in this one, now what we are going to do, we are going to replace in this expression, जो हमारा पहले ये expression था, we are going to replace, this is j of omega, we are going to replace this s j omega with this expression, and we are going to see how much magnitude we are going to have, because our condition says at omega px our magnitude should be less than 1. तो हम देखते हैं कि अगर हम इसको condition को apply करें, can we make the system stable or no? So if you just plug it back, just plug it back the numbers, we are going to have this one h of p जो हमारे पास point था should be less than 1. h of p अब वो point है phase crossover frequency का. This means we can represent gm rd whole cube divided by 1 plus we can safely write, if we were just want to write the magnitude now, we can safely write it's going to be omega px divided by omega p whole square, and this one is going to be in the cube form. Then this should be less than 1. इसको जरा देखिएगा. Is there any concern in this one? I'm just finding this HP point जो हमारे पास ये था, this HP point. इस point पे I am finding the magnitude, and for our condition this value should be less than 1. That's why we are putting this as less than 1 here. ठीक है? Might be that this might be more helpful if you just plug in the numbers yourself, but I'm just at this moment doing, but make sure after the lecture when I will upload, just do one time yourself with the hand calculation. If something is not clear, it will get clearer. So if we just put the values of omega px and omega p relation, which is omega px is equal to under root 3 times omega p, we will end up in something from this equation that gm rd whole cube should be less than somehow 8, or GMRD should be less than 2. So that if we are able to make some such scenarios, we can ensure the system is going to remain stable at a phase crossover frequency. But this meeting this condition is very much difficult. This means the system is going to have very much small open loop gain. आप लोग ये देख सकते हैं gain is very much small, it's less than 2, meaning the gain is already almost 1. अगर आपके पास gain उसका unity हो, then the system can only be stable in this current circumstances, otherwise the system is not going to be stable. या आपको कुछ circuit के साथ करना पड़ेगा. You need to add some capacitances, you need to add some resistances, but naturally what it's saying that bring this gain, जो 20 log h of g omega था, इस gain को काफी नीचे ले जाओ, which is equal to ये 0 dB है, तो almost इसको 0 dB पे ले आए, then the system is going to be stable, otherwise the system is not stable. ठीक है? ये clear है बात? If you feel something is not clear, I would highly recommend all of you to go through the example 12.38, and if something is not clear, just please update me. We can do this in a Q&A session on Friday, because this is very much important concept. That how and why the system is not stable and why we are trying to make it stable. Right. I guess we have to cover the topic for of the phase margin and then frequency compensation. We have next topic of phase margin and frequency compensation left in this chapter. Phase margin basically tells us how much margin we have to make the system stable or marginally stable, and the frequency compensation, if the system is not stable, how we can make it stable. Currently, we talked about very much crude way, that is not the realistic way to make a system stable, because this is not realistic. If somebody says make your gain as 0 dB and the system is stable, I want an amplification. Then if I'm not getting amplification, what's the point of even having a gain? Okay. So I don't want that way, I need a proper way, and that's going to come through frequency compensation. These two topics we are going to cover in the next lecture. And we will stop, I guess, now, since we are going to have a quiz time. So what I'm going to do, I will upload the quiz on LMS, and you will upload your solution, scan it, do that on your paper pencil, take a picture and upload on the assignment tab in the quiz 5. Within an hour window. So just don't try to take much time. The overall duration is going to be less. So try to finish it as early as possible. Any other concern? If we have 2 minutes, if you want to say anything, otherwise I'm just going to upload the quiz and then you can, all of you can start after that.
Sir, next two topics, and will these be covered on Friday or Monday?
No, we will cover on Monday. Friday will be just a QA session. Okay, if you have any queries, we can repeat the things, but these topics are going to be covered on Monday, not on a Friday.
Okay, sir. Thank you.
Okay, so I'm going to end the meeting now, and I'm going to upload the quiz, right? So if you have any question, you can just send me an email and we can discuss on the Friday, or we can discuss offline. Okay. Okay. Thank you for now.